Hi, today we're going to look at the truss. And, you see a bunch of triangles, structures, those are truss. You went to Walmart, you look up, you see those triangular structures, that's truss. And you drive across the bridge, you see the structures, the piers and columns, and that's supporting the pavement that's made of truss. And then when you go to Eiffel Tower and you see that structure is made of truss, you see all of them. They all share one common feature. They're all made of those triangles. Why do they choose triangles? Because triangles are very rigid. Like for example, if you have a square and you could potentially shift right into different deformation, but triangle is very rigid. That's the reason why. Then we know this truss has been commonly used in our everyday engineering design. And so here, that's the reason we're going to look at some truss problem. We needed to look at the goal is to find out the magnitude, the force in each member. Like for example here, this truss you see, there are how many members? You have 1, 2, 3, 4, 5, 6, 7. So AB is a member, right? BC is a member, etc., etc. All of them, there are, we said, the 7 members. We need to find the force in each member. What's the magnitude of them? Why is that important? Because you want to design something and choose the geometry or choose the right material to make sure it's going to be hold on to that force experienced by each member. And now, if we were looking at each member individually, for example, if I look at AB, each member is actually called an axial member. Axial member, that means the force is along the axis. So in other words, it's along connecting from A to B. So either it's going to be in tension in this situation. If it's tension, which means it's pull the member apart, right? Or the member has been squeezed, being smooshed, and it's being compressed. So it's called a compression. And that's going to be a compression member. But no, regardless, either tension or compression, it's all along the axis, so it's axial member. If you look at it, essentially each member is a two-force member because there are 2 forces, one on each location. And due to 2-force member, the forces are equal but opposite and collinear, which means they are connecting from A to B. So this applies for other 7 members. So we talk about AB, BC, AD, BD, BE, CE, DE, all those 7 members. You can go ahead and figure out the force in each member. And the second goal is each member being compressed or tension? Is that T or C? Is that tension or compression? So that's our goal for solving statics problem. But not every single problem needs us to figure out the force magnitude in each member, right? They might just say solve 2 out of 7, but you can actually solve every single member. Now this is actually, we're going to use this example to solve it. In order to solve this, to achieve this goal, there are 2 ways to do it. One is method of joints, which is this video is about. The second method will be method of section. We will talk about in a later video. And however, I just want to give a heads up because when you are solving truss problem, even we learned method of section or method of joints, but be flexible. You can use them, combine different ways to do, because trying to solve some member might be easy to joints, might be some easy to do section. Okay. All right, so now let's get to solve this problem. How do we approach truss problem? First of all, let's look at our step. Our step 1, we're going to look at this entire FBD1. So instead of look at each individual member. First we're gonna look at this entire structure, just like how you did it for frames, right? So if I were drawing this entire structure, I will have something like that. And we will have to draw the force acting on it. We have this external force, 2,000 and 1,000 pound. And we also have at point C here, it's a pin support, so we're going to have CX and a CY. At E is a roller support, so we're only going to have this upward, so it will be just E or EY. Then that would be our entire FBD. Of course, we're going to have the dimension right here, right? Then in that situation, we'll have three unknowns, and we're lucky to have three equations for 2D equilibrium. So forces at the x direction, we'll have Cx. That's only force on x direction, so Cx is going to be equal to 0. You solve the first one. That's easy, right? Forces at y, then we'll have negative 2,000 going downward. We'll also have this negative 1,000. We'll have this E going upward, and we'll have this CY going upward. That's our Y. Then we'll solve the moment. Where do we do moment about? We do moment about C, right? If we do moment about C, we have this 2,000, and the moment of arm for that will be this entire length, which is 12 plus 12. And that is make it counterclockwise, so it's positive. Now let's look at another force here. We have 1,000 here. And the moment of arm will be just this. And that is only 12 foot. And that is also counterclockwise. So it's plus. Then we'll have our E. Then the moment of arm for that will be this length right there. And what is that length correspondingly? So it's a 6 foot. And that is make it clockwise, so it's going to be minus. All that equal to 0. So knowing that, we can go ahead and solve our unknown. We can go ahead and find our E value. So let's take a look. This is going to be 2,000 times 12. That's going to be our 24,000. Then plus 12,000, right? So that's going to be our 36,000. Okay, so 36,000 is going to be equal to E6, so our E going to be equal to 6,000. Is that right? Oh, no, because this is 24. 24 times 4, this is 48. 48 and then plus 12, that's going to be equal to 60,000. 60,000 divided by 6. Then my answer here should be 10,000. So we solve our E, and that's in units of Newton. When we get E, we can plug it in here to find our CY. And this is 10,000. So pause, see what you got. So we'll get CY as negative 7,000 Newton. And our CX is equal to 0. Okay. And now we have it. This negative, which means this force is actually going, instead of going up, is going downward, right? Again, we don't need to go change it because our FBD corresponding to this answer. Now, that's the first step. What's going to be our step 2? This method is called method of joints, which means you're going to look at FBD of each joint one at a time. There are how many joints here? We have joint A, B, C, D, E. So there are 5 joints, different joints. If we were looking at joint A, if we were just looking at joint A, that's going to be our FBD number 2. So this is going to be our joint A. So what you're about to do is you actually going to isolate joint A. When you isolate joint A, you basically cut around joint A. When you cut around joint A, you cut member AD and you also cut member AD, right? Both AB and AD has been cut. And when you look at joint A, it's going to have a force coming from AB and have a force coming from AD. So here is a rule of thumb. I'm going to write it down. Every single time when you cut a member, which we did when we did joint of A, you cut two members. You will have, when you cut a member, you will have unknown. What does that mean? It means this A is going to have an unknown of AB, right? Going to be this AB. We do not know what direction it's going to be. If we assume it's going to be pushing, this member AB is going to be pushing to joint A. What guessing? Or maybe pulling away, doesn't matter. And also at joint A, there's 2000 Newton right here going downward, right? So you have this 2000 Newton going downward. And you also cut AD. So it's going to be along that direction. And here you can assume instead of pushing into it, it's actually pulling away from joint. And that's going to be our AD. You create two unknowns. When you cut a member, you have unknown. And that's important to know how to draw the FBD of joint. And it's actually quite straightforward, right? Whenever you cut a member, you have a force on there. And either it's going to pushing into the joint or pushing away. It's all up to you. It doesn't really matter. You are guessing it. The calculation going to carry out the rest. So it's very straightforward. Now we just need to figure out the direction of AD here because it's slanted. AD, let's take a look. This is 6 and this is 8 and divided by 2, so it's a 3, 4. So we learned it's a 3, 4, 5 triangle. We can label that on here. 3, 4, 5 triangle right there. Okay, when we have all that, we can go ahead and write down our equations. So forces at x direction. How many, actually, pause for a second. How many are known here? Only 2 equations, right? Only 2 unknowns. So we just needed 2 equations. And do we actually have more than 2 equations? Normally we have 3. Because we have a moment, but there is no moment here. Why? Because all those forces going through what? The same point joint A. Now, you just had another discovery. If you are using the method of joints, you will have no moment equation because all those forces going through the same joint. So in other words, when you are trying to create FBD of a joint, you want to start with something when you cut a member, you have unknown. You want to start to cut only minimum of, like a maximum of 2. What I mean is, if I were to go ahead, say I'm going to cut B, then how many members will I cut? I will cut AB, BC, and BD, and the BE. I cut 4 members, and I create 4 unknowns, but I can only have maximum 2 equations. So 2 equations cannot solve 4 unknowns. So there's a particular order when you solve method of joints. So that's going to be the pattern 3 you have generated is you go ahead start with joints. When you cut with maximum of 2 members, right? Okay, so we're lucky. We start with A, we cut 2, and we can solve those 2 unknowns. Let's go ahead and do that. Forces at x direction, you have negative AB going to the left, and AD and x direction will be 3/5 of AD, and it's positive equal to 0. And forces at y direction will have negative 2,000. Then we'll have AD going downward as well. So that's going to be negative 4/5 of AD. That equal to 0. Then pause for a second, see what you got for this answer here. What do we have for AD and what do we have for AB? All right, so hopefully you got AD as negative 2,500 pounds. And when you have negative 2,500 from this equation, equation 2, equation 1, you plug into equation 1 with negative 2,500. So that's going to give you negative 1,500. So your AB will calculate as negative 1,500. Do make sure you go ahead and solve those so you can get the same answer. Then you got two magnitude solved, right? Remember, our goal is trying to find the magnitude of the force in each member. And we know now, we know AD and AB are 2,500 pounds and 1,500 pounds individually. Then remember, our goal is to find if it's intentional compression. Now we can go ahead and start to thinking about it. Based on the answer you have, AD, we got a negative number. So what does that really mean? That really means that at point A here, I have this 2,000 pounds. And AD, the true direction is basically going down here, right? The true direction there. And AB, the true direction, is not pushing into, it's actually pulling away because I also get negative. So I didn't guess right for either one of them, but doesn't matter because the sign negative taking care of it. And this is 1,500. And this is our AD, which is 2,500 pounds. That's our true FBD direction with the magnitude. Now let's thinking about, here you're going to use Newton's third law again. Newton's third law, a reaction have equal but opposite reaction. So think about where is this force coming from? Which member is pushing into the joint A? That's from AD, right? AD is pushing into the joint A. Now, joint A gonna do what? Joint A gonna pushing AD back. So if now we are going to draw the AD is in this orientation, joint A is gonna push that back, AD. And then of course, this side we will know have to be this direction to balance up this, right? So now let's look at it. Is this AD in compression or in tension? Obviously, AD is being squished, so that's in compression. Then you answer the question. Now you can go back here and say AD is a compression. Now we're going to thinking about the member AB here. Member AB is doing what? Member AB is pulling joint A away. And what do you think? If AB is pulling joint away, and joint A, Newton's third law, is going to say, I'm going to pushing you, bring you back, right? Because AB is pulling joint A away, and joint A gonna pulling it away. So in that direction, we all know this have to be the opposite, and that's AB member is gonna be in tension. Okay. If every single time we have to do this, it takes a while to figure out the compression or tension. So here, we're going to come with another important pattern. If, here goes, if the joint is arrow into, if it's into joint, or you can call arrow, if arrow is into the joint, based on the true direction, right? Is this arrow pointing into the joint? Then that's going to be a compression. If arrow, the true direction of arrow is away, from joint, and for this one, if it's away from joint, then that's going to be tension. This apply every single time. So go ahead, do that. So if we know this rule, once we know the correct direction, just using this rule, and it's very easy to figure out it's a compression or tension. Okay. So so far we got two members taken care, AB and AD. We know the magnitude, we know the compression or tension. Now we're going to continue to go. Remember we're talking about one of the patterns. We have to start with joints when you cut with a maximum of two members. And now let me ask you, do you think we can cut member B now? If we cut member B, we'll have AB cut, but we already just solved the AB, so that doesn't count. But we cut BD, BE, and BC, so we still cut three, more than two members. We cannot solve it because we can only have two equations. We have to hold down B. But what other members can we go ahead and start cut? Can we go ahead and cut D now? Yes. Why? Because we already solved the AD, and you just only have BD and BDE as two unknowns. So that's what we're going to do now. We're going to look at the joint D, okay? And in order to do that, so we're going to look at joint D. I'm actually going to copy this down so you can actually see better. Periodically I will copy it down. Okay, I think that's better. So we're going to look at our FBD number 3, right? And we're going to cut D, joint D. If you cut joint D, you cut three members, right? You have three unknowns, but like I said, we know the joint AD already. So that's our D. This is our BD. This is our DE, and that's our AD. So go ahead and copy down its orientation. There. Then we're going to figure out AD. AD, we already know it's 2500 in compression. And remember we said this trick? If it is arrow into the joint, it's going to be compression. AD member is a compression member no matter on which side, whether it's on A side or D side, because it's D side is also compressed. So in that situation, this is going to be using this rule, have to be pushing into there because AD is a compression member. So I'm going to highlight this because this is very important. Why do we have this particular arrow going that way? Now we have our BD, what we are solving. Again, you are making a guess which direction this is going to go. And how about we guess it's away from it, right? And let me think, how about DE? How about DE we consider it as pushing in there. So we have BD and DE, we're guessing this way. Now we're going ahead to write down our equation. Forces at the x direction, what do we have? Oh, we need to get our geometry figured out here first. For AD, we have done that before. We know this is 3, this is 4, that's 5 before. And how about BD? This is also 6, right? And this is also 8. So it looks like we got a 3, 4, 5 triangle as well. Okay, then let's write down. So forces at the x direction will have this, write down this is 2,500 pound. That's our AD. So it is going to be 3/5 of 2,500, and it's pulling to the right. And then we have BD is also pulling to the right, and it's 3/5 of BD. Then DE is going to just pure left, so it's minus DE. That equals 0. Then we have forces at y direction. Forces at y direction, AD have a y component, is 4/5. 2,500, and it's going downward, so it's negative. Then BD, we have 4/5 as well, and it's going up, BD. that equals 0. Those are the two equations. Then we can go ahead, solve that. What's going to be our BD equal to from equation number 2? That would be just 2,500 because they have the same fraction, 4/5, right? So BD will be 2,500 Newton. And plug BD back in equation number 1. What will we get? So pause for a second and see what you have. So here we'll have 3,000 pound. Okay. So once you get those two, remember we have to figure out the direction. We got positive number, which means we guessed right. When we guessed right, and we're going to just use this pattern here. BD is pulling away, the arrow is away from joint, which means it's in tension. DE is pushing into the joint, which means it's in compression. So we have another two solved, right? So it's getting easier and easier, right? So let's make a mark what you have already solved. You get AB down, you get AD down, and you just get BD and DE. So there are only 3 left. Now, can you go ahead and cut joint B now? Yes, because the only 2 unknown will be BC and BE, because AB and BD already solved. Then can you go ahead and cut joint E also, perhaps? Yes, because you cut 3 members, but you already solved DE, so BE and CE is the only 2 unknowns. Then can you go ahead and cut C then? Yes, you're only going to cut BC and C. So there's no order anymore. You can just go ahead and solve any order to solve those using method of joints. Let's go ahead, just choose one. Why don't we go ahead and choose point, what do we think? Let's choose point to joint B then, FBD number 4. If we go ahead and use FBD number 4, what do we have? We'll have joint B. And we cut around it, we cut 4 members, right? So first member we cut is AB. And now we have to go back to see what we found for AB. AB is in tension. Tension will be away from that joint. AB is magnitude 1500. So using those rules, using those patterns or tricks, whatever you call it, it's going to be really helpful. AB is 1500 and there's external force that's 1000. And the BC is what you cut. And if we're making a guess, it's going to be this direction. Then we also cut BD. BD is in tension, which means it's away. So it's going to be that direction as well. And BD, what we have here is 2500 Newton. And then we also cut BE. BE is something we haven't figured out yet, right? That's going to be unknown. If we're guessing, it's going to be if we guess this direction away from the joint. So that's what we have here. That's our FBD of our joint B. Having a right FBD is going to get you on the right path. If FBD was not right, the answer will not be right. So take some time on that. And now how about we solve it then? Forces at the X direction. We'll have BC, positive, going to the right. AB, which is 1500 minus. Then we also have this 2500. Again, we're going to put our dimension there. And I believe this is going to be 3, 4, 5. Same thing for BE here. It's 3, 4, 5. Knowing that, we can write down our 25. This BD X direction is going to the left. So it's negative 3/5 of 2500. And the BE is 3/5 of BE, pulling to the right, plus that equals 0. Then forces at Y direction, what do we have? We have this negative 1000 going downward, and BD is also going downward, 4/5 of that 2500. For BE is also 4/5 of BE. It's going downward, minus 0. So we have all those equations. From equation number 2, we can go ahead and solve BE. Let's see, so that's going to give us 2,000. And together negative 3,000. All right. Then, so BE is going to be equal to let's see. So I use calculator. My B is negative 3750. I've been using Newton, by the way, but the problem is given in pound, right? All of those. So make sure here I need to get my unit right. So that's pound, pound, pound. Okay, so this is going to be pound. All right, then plug this value into equation number 1. Then let's see what we have for our BC. That's going to be 500 times 15. That's going to go times 3. That's going to be negative 1,500. And bring that in there. Okay, so here my FBC is going to be 5250 pound. All right, now we need to figure out the direction, right? Tension and compression. BE, we get negative value, which means the true direction is going to be pushing it in. That means it's in compression. BC, we got positive, which means it is indeed the right direction. That's away, so that's in tension. So you got all those two figured out. So what is the only member we haven't done? The only one we haven't done is going to be our CD. So in order to do that, you can go ahead, look at our FBD number 5. That's the last one, right? So if you look at joint C here, when we cut around it, you cut BC and CE. However, we already know BC. BC is in tension, so in that situation, it's going to be away. That's BC. That's equal to 5250 pound. Also, we have CE, and if we're guessing is going to be pulling that direction, pushing into it, so that's our CE we're solving. And don't forget, since it's connected to the external part, right? It's going to be what we have over here, CX and the CY. CX equal to 0, that's our reaction support, and the CY is going to be, here it's at a negative 7,000, corresponding to this FBD, right? So the true direction, the reaction support is pulling C downward 7,000. So then joint C is going to have a downward 7,000 pound. I'm going to highlight that because that's important to why we have downward. If we don't get the correct direction here, right, with what we already find, our answer will be, cascade, will be like snowboard to be wrong. Make sure the direction is right. Now, knowing that, we can go ahead and write down our equations. Our x direction, we have this negative 5250. Then our CE again, let's go ahead, it's 3/4 triangle as well, and plus our 3/5 of CE, that equal to 0. Our fourth set of Y, we will have this downward negative 6,000. Then we'll have this 4/5 of CE going to upward equal to 0. And you notice something? We don't even need the two equations to solve this one unknown. Either forces at x and a y going to give us the answer, and this should give us the same answer. So I'm just going to try 15250. Going to be times 5 divided by 3. We'll have 8750. That's my CE, and that's going to be positive value. And if I were using the second equation, 7,000 times 5, then divided by 4. We get the same answer. Yep. So that's our CE. And CE a positive number, which means this direction is correct. That's pushing into the point. That's going to be compression. All right. So far, we solved the truss problem. We solved this one, and we know our goal is finding the magnitude. We started with the entire FBD in step 1, find the reaction support. Then we look at individual joints and using those rules we have generated along the way. And to get it, one thing, this is very tedious. One thing, if one answer is wrong, and that's going to lead the other answers wrong as well. So be really careful using method of joints, and it's like a domino effect, because your next FBD, your next joint is built upon your previous one. All right, I'll see you next time. Bye now.